So bad.
A Jeep?
Yeah.
Jeeps are both incredibly unsafe and they break a lot, so I would not recommend a Jeep.
Or your white.
Alright.
I do not want to.
Okay, these other two things I'm going to run through really, really fast, so please give me your attention. By the way, these are things that would have been one-day lessons on their own anyways. They're very simple. They're not complicated to think about.
Your mom.
So, I always forget that meme is on here. So look, I'm going to go through a brief history of gravity here. I'm going to go through it at like a super accelerated rate. The reason is that like there's this, so this is another lesson that I tend to like to do life lessons in, and I don't want to give that up, so I'm just going to do it really fast, okay? And then we'll get to what you need to know at the end, which is one equation that's very simple.
How do you know how heavy the black hole is?
How do you know how big a black hole is? I just know your mom's a lot heavier, so, you know, that's
Boom.
all I need to know. It's fine.
Technically.
All right,
Let's alert out.
so let's run through it, right? So here's the deal. I like to do this lesson because I think that the history of gravity is a great time to talk about what some people see as a bug in science that's actually a feature. So there's this thing that happens, and it seriously makes me want to scream, where like idiots on the internet will see like scientific consensus change over time, and then they'll be like, oh yeah, just trust the science. It makes me want to kill people, like it really does. It's like I'm not a very violent person, but the idiots on the internet that say that, I just want to find their home and burn it down. I'm just kidding. I'm just kidding. So I don't know. So look, here's the deal. There is a thing in science that science is designed intentionally to respond to new data, right? That's what science is. It's making observations, collecting data, making inferences based on that data, testing those hypotheses that you come up with and all that kind of stuff, right? Using those test hypotheses to build models, and then responding to changes in research and data and adapting your model. Like that's what science is there to do. That's why we use it, is because it's always open to new information and adapting to that new information. But sometimes what we see is that some of the more fringe things end up being altered, and then you have idiots who don't understand science and don't understand that like that's kind of the point of science, is that I make the best choices I can with the data that I have, and so as I get new data, that means it's better. So science never gets to the point where we're like, yep, we got it all figured out. We kind of figure out like, okay, here are some concepts that we feel very confident in, and here are some concepts we're not so confident in. And I think the scientific community is very open about that, right? So like one of these things that's been like an issue has been climate change. Because over the past like 50, 60 years, climate change data has been really exploding, and we've been able to learn more about the nature of climate change. And as we've taken more data, we basically, we keep figuring out that it's worse than we thought, is basically what's been happening. But what happens then is that people take that idea of like, all right, they keep figuring out it's worse than they thought, and instead of like realizing that the new information is better, they instead claim that it's like scientists being wishy-washy. And it's like, no, that's not how it works. It's like, we collected data and we said, yeah, the earth is heating up, we're not sure that humans are causing it. And like, scientific community was really open-handed about that for a long time. And then like, it got sort of like, okay, the earth is heating up and we're pretty sure humans are doing it, right? Like we got data, we think humans are doing it. And so we became a little more close-handed about it. And now as we collected more data, it's like, okay, yeah, the earth's heating up, humans are definitely doing it, and we probably only have about like 100 years of good times left unless we start to change things, right? And by the way, you only have about like 20 years to correct your behavior to make sure we avoid that not so good times down the road. So as we've collected more data, we realize the picture is worse, and we're adapting the way that scientists adapt the way that they communicate with people based on that. And what happens is, somebody who doesn't understand science, they look at that like progression of ideas and they say like, well, you were wrong before, so why would I trust you now? But what they don't see is that that progression has actually like been pointing in the same direction the whole time, right? It's just kind of like getting worse. Point being, I want to talk to you about the history of gravity because it's a good case study in like how science works, okay? And the big picture here is that the way science works is that I make the best models I can with the data I have, and then as I get new data, I adjust my model. And it's very rare that you actually have like a big, pretty well studied idea change, right? So like at this point, I would count climate change as one of those things, right? Like we understand climate change pretty well. No one's gonna come back and say, you know what, we were totally wrong. Those guys selling oil were right. It's totally fine, right? Like that's not going to happen. Sorry. What might happen is we might say, you know what, it's not quite as bad as we thought, but we're not going to come back and revise the whole story. Because that's the other thing that happens with science, is as I build more of a data collection, I become more firm in certain ideas that I have lots of data to support. Does that make sense? So what you see then is like fringe of the model will change, but not the model overall. Anyways, let's talk about gravity. So real quick, we're just going to go through a quick history of gravity so you can see like how has the human understanding of gravity changed over the past like several millennia. So as we go through it, in ancient cultures, basically they didn't know what the heck was going on, right? They were just like, yeah, there's stars in the sky, that's cool. Except what they really thought was that the stars in the sky was like a revolving painting on the sky that like turned in the air. They didn't really understand what it was. And so you have this interesting concept of like what they call the dome. And for any of my fellow Christians out there, it's actually interesting when you like read the Bible, it talks about the stars in the sky. It actually uses the term the dome because that was the understanding at the time of those people, was that it was a dome in the sky, like literally. Interesting point, right? So anyways, we didn't understand what was going on very well, and so what we did was like, because we didn't understanding, we tried to associate it with like, you know, that star was in the sky and my crops died, so, you know, that God must be mad at me, right? Like, that is basically what would happen. And so you ended up with ancient cultures attaching, like, religious meaning and predictive meaning to all sorts of things in the stars, which brings me to white women, right? So we've got the zodiac, right? So the zodiac is a thing that, like, we know isn't a thing, right? But it's kind of fun, and it's on the internet, so, like, we do it, right? So we've got all these astrological signs. I put this up here because, like, I want you to understand what it is and why it's silly that people would think it is real. Because, like, and here's the deal. There's different categories of people, right? There's a lot of people that they do the zodiac because it's, like, kind of fun, right? Which is fine, right? There's a lot of people that do the zodiac because they actually believe that it's true, and that's stupid. So what the zodiac is there's like these, I forget how many I said. 12. There's 12 astrological signs, right, that are just like constellations that happen to be in the orbital path of the sun, right? So that's a bad way to put that scientifically, but I'm going to let it slide. So what happens is one of those things won't be visible in the night sky because it's like behind the sun, right? And so that would be the sign of that time. Does that make sense? So like if you're a Capricorn, I'm a Capricorn, that means that when I was born, the Capricorn was behind the sun, which means you never saw the Capricorn at night in the sky. Does that make sense? So it's like, hey, that one's missing, so that's your sign. All right, so, whoopsies. So this is a model of what that looks like, right? So you've got, it's fine, don't worry about it. So if you look what that looks like here's the Earth, right? And so at the time that, you know, we would say that you're born and you're a Leo, it's that the constellation's over here, and we never see it throughout the night sky, because as it's revolving, you'll see kind of these dimly, because the sun will still be essentially out, and then you'll see like Aquarius in the middle of the night. So it's just like that band is constantly revolving around the Earth, but you don't see all of them. Does that make any sense? Okay, anyways. Now, we get to a point where like we start to collect some good data, which by the way, I'm glad this is becoming a thing that people know more about, but for a long time nobody really talked about it. Like the Muslim cultures in like Egypt and the Ottoman Empire and all this kind of stuff, like for millennia, did amazing work with all of this stuff, and they deserve a lot of credit for it. Unfortunately, they don't get any credit because we live in a world that's run by white men, and so you end up hearing about the white men. It is what it is, right? Like it's a European-centric world because they were colonizers and they changed everybody's history. It just is what it is. But point being that we don't get to hear about all these amazing people that did things around the world, right? But that's where we get a lot of our early understanding of the solar system. So we had this thing called the geocentric model, which is where we said, hey, what makes the most sense to me is when I look in the sky, I see everything revolving around me, therefore me must be the center and everything revolves around me. It's a very common sense thing to think, right? There's a bit of a problem there though, which is that there's this issue of retrograde. So some of the stars, they don't move the right way all the time, right? Like if you look up in the sky, they're all moving this way, except like that one star, it's not doing the right thing, right? And so if you watch here, you can see two of them that they change directions, right? Do you see that? It was going that way and then it changed direction, goes that way again. So then it's like, well, what the hell is that thing? That's not fitting my model. So then what we do as humans is we collect a bunch of data and we try to explain what it's doing, right? By the way, we would call those things planets at this point. So the first idea we came up with was something called epicycles. So we're like, okay, everything's orbiting around the Earth, right? Except those things are orbiting around the Earth on a circular orbit. So it's like kind of doing this thing, right? And that would explain why every now and then it changes directions, which sounds stupid now because you're like, well, something had to be causing that, but they didn't understand anything back then. They were just doing the best they could, right? So they get this idea of epicycles, which is kind of brilliant.
Teachers, the students are doing such a great job. We are moving quickly. We are ready for 9th grade, and we'll go ahead and move the rest of the schedule up about 5 minutes.
All right, so that was the next thing we came up with, right? 'Cause it's like, hey, I looked closer, I saw more stuff, here's an idea. Here's, by the way, an animation of what that looks like. So if it's on a little circle around a circle, it does draw that shape, right? It's like, yeah, that makes sense. So that works until I collect more data, right? I collect more data and I realize, nope, that's not how it works. That couldn't be how it works because it doesn't fit my data, right? So you end up getting these people that they can collect really good data because they've got these cool instruments. Like this guy Tycho Brahe, who's really good at building telescopes. He's like super rich dude, doesn't have a nose. So he like gets all these telescopes and does this really cool stuff with it, right? And we get this amazing data and then we're like, hey, that data doesn't match this model, so our model must be wrong. Does that make sense? Okay, so we get that data, we see our model must be wrong, and then you got Copernicus who's like, hey, yeah, we're gonna do this, right? Copernicus, by the way, we say the church didn't like him, that's actually all overblown, like by a lot. It's not that big of a deal. He actually had the church's approval to publish his writings at first, and then it was like a political thing that happened down the road, so it's not that big of a deal. Anyways, we get to this heliocentric model, which is where the sun is at the center, and what we say is like, hey, what's really happening is the sun is here, and we're going around the sun, and there's other stuff in the sky that's also because we're going around the sun and turning, that's what makes it look like it's all moving the way that it's moving, but it's actually relatively stationary. And that is where we then land. We're basically the same model that we have now, right? Like it makes sense, it fits the data, it's all really good until, oh wait, there's another problem. Oh wait, hold on, here we go. So here's what this looks like. Now this explains the planets, right? Because what we say is that those planets, they're actually other Earths that are like orbiting the sun together. And so like what happens is that retrograde happens when either I pass it or it passes me because of something called parallax, which this is illustrated here. So that explains everything. We're in a good spot until other stuff. By the way, Kepler makes some laws. It's not that important for what we're doing. But what's important to understand is at this point we still don't know what the heck's going on, right? We don't know why this is happening. We're just like, hey, these things are doing this thing and it's kind of cool. Until good old boy Newton steps in the picture and he's like, hey, I got this idea about gravity, and he comes up with all this stuff. The whole Apple thing is not a true story, by the way, but that's fine. So Newton comes up with this idea. By the way, this is an equation you should write down. So I'm going to pause here in a minute. But Newton comes up with this idea that, you know, what's really happening is that all matter is attracted to all other matter, and it's that attraction that's fueling all of these interactions in the solar system. Is like the sun is this big thing of matter, and all those planets, they're really just like projectiles that are moving really fast, so they never actually hit the sun, they just kind of move around it. Now, here's an equation for that. F equals gmm over r squared. That is the universal gravitation equation. That's the thing that you need to know from this lesson, but it's a simple equation. You just plug in numbers, right? It's not that big of a deal, which is why I'm doing this so quickly. So, anyways, that's that. I'm going to move on. Did everybody get it written down? Okay, so moving on in our story, that's really good and all that, and look at this dude Cavendish who does an experiment, which, by the way, we don't have time to watch it. This G thing, we didn't actually know what that was for a while. We just knew that this was a proportionality, right? It would have been like the force must be proportional to the masses in the radius, because that's what I could study from a long way away, is proportionality. I couldn't actually collect data and put numbers to it until Cavendish made this experiment and basically accidentally found G, but I don't have time for that story. So that sounds really good until we get better instruments, and this is like, I believe, if I remember correctly, It's like in the late 1800s that we're like, hey, this is all really good, but now I've got really good telescopes, and when I look up at the sun, what I see is that Mercury is doing this thing called precessing, where it's like changing its orbit just a little bit every year. And our current understanding of using forces, it doesn't explain that, right? Like, this is a good model except for this one thing that it doesn't explain, and now that's a problem. Enter the guy, the original OG man, Isaac Newton. No, damn it, shoot.
Einstein.
Crap, I said a bad word. Einstein. So Einstein comes up and he's like, hey, the reason this isn't working is actually fundamentally at its core, we don't understand space at all. Because space and time are not different things, they're the same thing. And if they're the same thing, then that thing, for some reason, gets bent by gravity. And that's where we get into all this relativistic physics that we now understand to be true because it matches all of our data. And so now we're at the point where we say, okay, this is really how things work, is that gravity's not really a force. It's actually that matter has this property where matter bends space-time. When you have a lot of matter, it bends it a lot. And that causes things to like slide into each other, basically. It's a really way too low-level explanation, but it works. So we don't have time for the video. So we find all these reasons that Newton was wrong, right? Couldn't predict gravity, couldn't account for Mercury's precession, a wrong understanding of inertial frames of reference, and doesn't consider space to be part of time. So Newton's really wrong, but we actually still use his stuff, right? Like, we still use that equation that I showed you, and the question then is why? And it's because that model, though we know it's not entirely correct, it's actually still really useful, right? The reason it's still really useful is because it's very simple, and it works really well for like 99.9% of things that humans interact with, right? Like, it still works for those things. So we don't throw the model out entirely, we just kind of like put an asterisk on it, and we say like, hey, this works for these times. Because I can show you the equations. You don't want to be doing relativistic physics calculations for everything. That would be really stupid. So instead, we use Newtonian gravity for most things. Like when NASA is like planning space flights out into space, they use Newtonian gravity. They don't use relativistic physics. That would be way overkill. So what we find though then is we have to put like rails on it and say like, all right, you can use this as long as you stay within these parameters. And those parameters are when you have a relatively small mass. And what we mean by that is like a mass smaller than the sun, right? Which is most things that we interact with. When you're moving at less than 1% of the speed of light, which seems like that might be slow, but the speed of light is like 300 million meters per second. So it's like stay under 3 million meters per second and you're good, which is insanely fast, so that's fine. And when we need extreme precision, right? So if I'm doing something that's going to change my calculations, ruin everything, then I don't use it. And that's really the lesson, right? So the point of this lesson is that we can see as you collect new data, you alter your model, you add in new things to respond to that new data, and that's not a bug, it's a feature. That's how we can know that science is making the best decisions it can with the information we have at the time. That doesn't mean it's right all the time, but it's the best we have, right? And the scientific community is built on transparency with data and all this kind of stuff to make sure that what we have is fairly reliable. And it's an ethical thing that scientists have to adapt to new data, right? Which is why we should trust them the most, because they don't get like stuck on these little arguments, right? Because what they care about is the truth and trying to get close to the truth. Does that make any sense? Mm-hmm. That's the lesson. All right, I've got like 3 minutes, which is not enough time to talk about circles. So we'll do that tomorrow. I think tomorrow I can talk about circles and simple harmonic motion. So I'm going to stop today. Do you guys have any questions about this like light speed run through that I just did here? Okay, the important thing you need to know is that F equals gmm over r squared equation and how to use and plug in numbers there, right? So the two m's are the two masses. The r is the distance between those two masses. And the g is a constant that's on your formula sheet. So you just got to plug in numbers. It's a really, really simple thing. Make any sense? All right, that's it. I hope you enjoyed hearing me ramble very rapidly about stupid things in science.